Ready? Good. Hello and welcome back to Calculus 3. This is section 13.2 on integrals or double integrals over general regions. So far we were confined to rectangles and squares as our domain, and all of our, as I described as a cookie stencil, all of them had the flat cuts right on the sides going straight down, but the domain was either a rectangle or a square. Now it's time to kind of round this domain and have a different type of a cookie cutter, right? So say that you have domain, which is, we know, xy. Say that you have a parabola, which we know it's x squared, and then let's say a linear line, and this linear line is x plus 1. So now that would create a shape for a region that it's no longer rectangle, right? And now you will have a shape. Now, what is this shape? This is a shape of a stencil that you are pressing into the cookie dough, right? So whatever shape you have will have its sides fit into this region, and then the top is going to be whatever wavy f of xy you have. So our cookie stencils now will be defined by these functions. So what would be the integral that we are dealing with, the double integral? Well, first off, they are computing the volume, right? So volume is equal to, and we say double integral over region R, f of xy dA, is going to be the integral from a to b, and then integral from g of x to h of x. You see, now you have functions in limits. Times f of xy dy dx. Or volume is double integral r fxy dA being cd, and then g of y, h of y, fxy, dx dy. Aha! So what is happening over here? Do we all see that changing order of integration is immediately a living nightmare? Because look at your functions on a second integral. If you swap the order from dx dy, those functions have to swap from g of x to g of y. Right? Can you do that all the time? No. Right? You can't actually do it all the time. So we have to worry about much more stuff immediately than what we used to do before. But let's start off easy and deal with just the normal stuff first. So, oh, this is actually an amazing example. We should talk about this. Okay, let's talk about this one. So we have function f of xy given as 2 plus 1 over y. And region R is bounded by, and now we have functions y equal x, y equals 8 minus x, and y equals 1. So it's bounded by these three functions. Now all these functions are linear lines. Do we all agree? What kind of geometry you have if you have three linear lines? Triangle, exactly, right? Let's draw this domain and study the domain first. That is going to be your first step in chapter 13. The entire chapter. You always start drawing the domain and analyzing that first. Because you need to have your limits for the integral, and they only come from the domain. Because domain defines the integration limits. Guys, please go. We're going back to Calc 1 just for a single flash. Do we all remember this picture? Do we all remember that the integral for area was a to b f of x dx? Are we all cool with this? Yeah. Right? Look at your limits over here. What is that? Is that the domain? That's the domain, right? Your integral limits are strictly defined by the domain, the shape of the domain. If you are unable to understand the domain, if you're unable to draw the domain, if you're unable to analyze the domain, you can't do any of this stuff. You have to focus on drawing proper domain. Calc 1, easy, not an issue, right? It's just a to b. That's your domain, so a to b. You find your area, you're done, right? Right now, we are dealing with functions that are in your domain. Your domain is two-dimensional, so your domain now is going to be, we draw what we have. I have, oh, come on, 8 minus x. So I gotta go all the way up to 8 here. So let's say this is 8. 7, 6, 9, 8, 7, 6, 5, 4, 3, 2, 1, and finally x-axis. All right, I guess the engineering rule of draw big prevails over here. I have y equals x. That is going to be, and you know what? I'm going to use light. I'm not gonna press as much. This line, this is perfectly straight line. It's just your eyes are terrible, so you should check that out. Y equals x, and we have 8 minus x, so that's going to be this. Clearly going through 8 on x-axis, and y equals to 1. So what do I get here in red? This. There we have it. Region R. It's a triangle. This is your cookie cutter stencil. All right? You press this triangle, you are getting triangular cookies with a wavy top of a cookie that looks like this, whatever that function is. So, what do I have? Well, we start from first figuring out if we want dx dy or dy dx. That is always your first thing to deal with. So question number 1, do we want dy dx or dx dy? Why is this important? Well, first off, order of this matters because we've seen a problem where one way it gives you simple integration, the other way it gives you integration by parts, right? So that could be a factor. What else could be a factor? Well, it could be a factor one integral of two integrals. That's also one. It could be a factor that one of the ways would not be possible because you can't integrate at all, right? Let's say you get just e to the x squared. You can't integrate that, right? So there are certain cases where you really have to consider. In some cases, it won't matter, right? So now what do I have? Now this is the key. If you understood the story of representative rectangle in Calculus 1. And if you understood that very well, then this over here should be a walk in the park. If you don't know the story of dx on Calc 1, well, you'll have to learn that first. So, I know I'm drawing this on the board, but it's Calc 1 review, so I can't really fit it over there. In Calculus 1, you had your function a to b, and we said representative rectangle delta x right here. So when you write your integral a to b f of x dx, you look at this thing and you see that representative rectangle swipes from a to the right to b. So that's why your limits are a to b. And then the height of the rectangle is from 0 to function f of x, which is why this over here is f of x minus 0. Then we improved this to two curves, f and g, and we had the intersections define a and b. So now, I mean, you can cut it sooner if you want to. So now your integral, again, representative rectangle, it's always representative rectangle is in the mix. Representative rectangle goes from A to B, and then the top of the rectangle is writing F, the bottom of the rectangle is writing G, so F minus G dx. This was your formula for area between two curves, right? Do you see the representative rectangle handles 100% of that stuff? It's the representative rectangle that travels from A to B on X, and it's a representative rectangle that is stretched from F to G or from F to 0. Do we all see that? Now, what happened when you had a piecewise function in Calc 1? So your piecewise function was some kind of a linear, and then turned into some kind of polynomial. And you wanted to calculate area from A to B. Well, you draw your representative rectangle, and when you draw your representative rectangle, you quickly realize that your representative rectangle is going from 0 to a linear, but then when it's on this side, it's going from 0 to quadratic. Right? Well, you can't put that in the same integral. So what have you done? You break this at some value c, so you have the integral a to c, which was, call this f, call this g. It was f dx, and then you had plus integral c to b of integral g dx. So you broke the domain, right, into two separate integrals, because you can't go 0 to f and 0 to g in the same integral, because which one do you put here, f or g, right? They both need to be there. So you just do one at a time. So representative rectangle is the one that always swipes from left to right. When I say swipes, that representative rectangle exists in all locations, just like electron exists everywhere at all times. Right? So right now, you have representative rectangle at A, that's the most left representative rectangle can be, and then it ends it with C. It stops there because it is all of those representative rectangles have 0 on the bottom in common with a linear on top. And then at C, it switches 0 on the bottom and quadratic on top, right? So we have to have two integrals. But over here is a single integral, because it's a single integral, because the bottom always writes g, the top always writes f, and that's good, because when it's always writing the same function, I can just go for the entire a to b with the same set. Are we all agreed on that? That's your Calc 1. So now, what do I have over here? Well, whatever is the outside dx or dy, when I say outside dx or dy, I'm talking these puppies right here. Whatever is outside dx, dy is your main one. Main one. And then the inner one is the, whatever, secondary, whatever you want to call it. So now let me see what would happen if dx is my main one. Well, I draw, you guessed it, right? Representative rectangle for dx. Do we all see that as this swipes from 1 to 8, from 1 to 7, do we all see how it's going to switch at 4? So what is that saying? No. 2 integrals, right? Okay, so this one is 2 integrals. How about this one? Let me draw dy. Now dy is going to swipe up. Do you see that the sides are always writing same functions? Now that one is 1 integral. This is the type of analysis that you get when you have the picture, when you have clear understanding of what your domain looks like, right? So now you're considering, all right, well, do I want to do 2 integrals or do you want to do 1 integral, right? 2 double integrals or 1 double integral? Well, presuming that you are normal, right? You would want to do 1 integral, right? So I pick this one. So what do I have now? I have my double integral. I know the function that I need to stuff inside, which is 2 plus 1 over y. Make sure you put these parentheses. And I know my order. It's dx dy. Because I analyzed it in such a way that I get to use only 1 integral. Now, as soon as I pin this part over here down, I immediately know that these must be my y limits and these must be my x limits. Now, x limits is actually x as a function of y, right? Let me see it right here. Do we all see it? If the outer is dy, then the outer limits are c and d, and the inner limits are x. But look how great this is. The inner limit is x, right? Would you agree that this is x equals as a function of y? And x2 equals as a function of y. Please use that common sense as you are setting these up. So c and d belong to y limits, and x are x1 and x2. But x1 as a function of y, and x2 as a function of y. Because these are lines, right? They could be parabolas or cubes or whatever else, but right now they're parabolas. I mean, linears. Great. We take a look at our picture to come up with our limits. So what do I have? I have y limits on the outside that are clearly going from 1 to 4. Are we agreeing to say clearly going from 1 to 4? Are we all 100% clear that the outer limits are 1 to 4? Because the representative rectangle dy is going to start at the lowest point, which is the red line on the bottom, which is 1, and take all of the values all the way up to the tip of the triangle, which is at level 4. So we all cool 1 to 4 on the outside? Perfect. Now we are going to do, you remember right minus left? Yeah, now it's going to be right and left. Right is on the top and left is on the bottom, because we are going towards the y-axis. So what is the bottom limit equal to? Well, the bottom limit is this side of the line. And that side of the line is y equals x. So what's x equal to? y, exactly. So the bottom limit is y. Great. How about the other side, which is the upper limit? Well, we have that this function is y equals 8 minus x. What's x equals? 8 minus y. So we had to flip that. We had to flip that. This is very difficult to have everything in one shot. There we go. I had to zoom out, so it's now smaller, but at least you can see everything. So let me go through this one more time. Just make my pointer over here. Don't you love how, like, the only thing I use markers was to make a pointer. So we went through the analysis and we figured out that it's better to have dx dy because that gives us one integral only. We put dx dy there. As soon as we put dx dy there, that means that these are y limits. So y limits, you are looking at the y going up. So the lowest the dy can be is at 1, and the highest it can be is at 4. So 1 to 4. Then we have the x stuff, right? And dx stuff, I need x1 to x2. So x1 on the lower limit, that's writing this, and x2 writing that. So upper limit is this one. So that's going to be your 8 minus y when you solve it for x. And then, so I have so this is going to be now y1, y2, x1, x2, and y dx, x1, x2, y1, y2. So you can always see it. Oh, that's a question.
Shouldn't there be y, 2 over y, y to the y1, there are 2 y1.
Good. I was just testing and just passed, right? The attendance portion of the class. Very good. All right. And now we need to solve this, right? We know how to do this, which is do the inner integral first. So we have 1 to 4. Integrate this in respect to x. What do I get? I get 2x plus x over y. Right? Do you understand that over y is just a constant? And look at my limits. Hello, algebra. Right? You will plug these into x's. So 1 to 4. We have 2 times 8 minus y plus 8 minus y over y minus 2y minus y over y. All of that in parentheses, and I still have dy. Look how great this worked out, right? All of the variables that I have are y's, and I still have to integrate y out. So that's good. What would be wrong? You immediately see you are wrong if you have any x's left, right? Because now you have to integrate in respect to y at the end and just use 1 and 4 and be done, right? So that's that part. Let's do the ton of algebra first. We have 16 minus 2y plus 8 over y minus 1, when I separate into 2 fractions, minus 2y minus 1 dy. Right, simplify one more time, 1 to 4. I have 16 minus 1, that's going to be 14, minus 2y, and then plus 8 over y, and then I have to integrate that. So 14 is going to be 14y.
Minus 4y.
Oh, minus 4y, yes, thank you. 2y and 2y, so there's a 2y and 2y, so minus 4y. Yep. Now we have y squared, so it's 2y squared. And what's my integral over here? Eight over y? Very good. ln absolute y, right? Computed from 1 to 4. Plug in 4 everywhere. That's 14 times 4 minus 2 times 4 squared plus 8 ln 4. Minus plug in 1 everywhere, which is 14 plus 2 plus 8 ln 1. What's ln 1? 0. So this term dies. 14 times 4, very good, minus 32 plus 8 ln 4 minus 12, whatever, calculate something. 56 minus 32 is 24 minus 12, 12, so this is 12 plus 8 ln 4. And you can go ahead and calculate your decimals. This is about 23.1, just by looking at it in the book, obviously. Yes?
We just left it like this as the final answer.
That's perfect. Just leave it right there. I'm just, some people are really attached to decimals. They can't live a day without. So I say 23.1 to make sure that no one feels left out in class. I'm accommodating, right? Always. Great. Let's do more examples. Because this stuff is awesome. Ooh. Oh yeah. Why is this not working now? Like, why can't I switch? Something is happening somewhere, and see, has to be plugged in. This is what your cookie looks like. It has a triangular base, straight up walls, and then the top is like this. It's more like a tool for something to cut or whatever. But this edge is extremely sharp, right? As you can see, it's extremely sharp edge over here. Very sharp edge over here. This is very spiky, right? So this could be like a tool to cut something like, what's called the one that rotates with you put a piece of wood and then you can make a bat or something. Lathe, thank you, yes, lathe. So this could be a tool for lathe, for instance, that comes in and just like cuts through. I don't know what they look like, I'm just,
It kind of looks like that.
Oh, it does?
For like a metal lathe, that's kind of like what the cuttings are.
Oh, perfect, then yeah, yay. All right, good. So that's one of the applications right there. And you have seen the shape. Very important for me is to understand that you guys, you guys should understand the domain. There we go. Fixed English right there. Oh, that's later. That's later. That's later. Squeak, squeak, squeak. All right, here's problem 28 from the textbook. It says calculate the integral over the region R from x plus y dA, where the region is in the first quadrant bounded by x equals 0, y equals x squared, and y equals 8 minus x squared, quadrant 1. First quadrant. Procedure for all of these problems is always the same. You must draw the domain, otherwise you are doomed. So what do I have? Well, I have two parabolas. One opens up, one opens down, right? So I should be able to draw this quickly and efficiently, and then looking at the picture, decide if I'm using dx dy or dy dx, right? That's my first concern. So draw the, so I have a parabola that opens downward. This is the 8 minus x squared one, making this to be an 8. And then I have a parabola that goes up. That's the x squared one. And they want only the first quadrant, so I'm going to shade this and put big R inside. Great. What is the first thing we have to decide? The order of integration, right? So let's try so whatever is the second one is the main one. So I wrote dx dy first, so let's draw dy representative rectangle. What do we see when this representative rectangle slides from bottom all the way to the top? Two integrals right away. Right here is a split. Do we all see that? Left side of this representative rectangle will always ride x equals 0. But look at the right side. It rides x squared, and then it switches and rides the other one. You can't have that, right, if you want a single integral. It can't switch. It has to stay with the same function throughout. So, we are not happy with this one. Maybe the other one is going to be worse. We don't know, right? But at least I know this is two integrals over here. Let me draw dx. Is this better? Yes. This is much better. Because the bottom always rides x squared. The top always rides 8 minus x squared. Yay. Right? For the entire trip, it starts on the y-axis and goes all the way to the right up to that intersection point. What's the intersection point? Yeah, this is where you have to do algebra to find, because no one tells you what this B is. You all know your A is 0, right? You can see that. But the B, no one tells you that, right? So we are picking this one because it is a single integral rather than two integrals on the left. Can it be done by the other one? Of course it can. It's just much more work, right? Double the work, because you have to solve two integrals. Now I need the intersection point over there. That's going to be x squared equals to 8 minus x squared. You did this way too many times for your area between two curves and other cases. So now you're having that 2x squared is equal to 8, x squared is equal to 4, x equals plus minus 2. Well, minus 2 is on the other side. We're not using it. So we have that x equals to 2 is the one that we have to use for our limit. Great. I have my double integral, x plus y. We know that the order is dy dx. So my outer limits better be x's. Well, we know that that's 0 to 2. We just calculated the right point x equals to 2, where the intersection of the two functions is. And what am I doing for my functions over here? For the other limit, inner? X squared on the bottom, very good, because you see that the bottom of this rectangle is writing x squared, and the top is 8 minus x squared. Perfect. So we have our integral set up, and now it's the time for you to compute this. So deal with the inner integral first, and then deal with the dx next. So take some time to enjoy this. But just do it for some time. So this is just like a big annoyance, a lot of algebra, all right? Have to be very careful as you go about solving these.
So before you plunge it on the thing, I got times k minus x squared plus 3 minus x squared over 2 minus x cubed minus x over 2. Evaluated from a minus x squared over x and then minus x squared. So
all right, so the integral in terms of y is xy plus y squared over 2, computed from x squared to 8 minus x squared. And then we still have dx to deal with later. This is integral 0 to 2. Plug in for y, so we have x, 8 minus x squared, plus x to the 4 over 2. No, lies. 8 minus x squared squared, there we go, minus, this is x cubed, minus x to the 4 over 2, much better, dx. So deal with this algebra now. 0 to 2, 8x minus x cubed, plus, now this is 64 minus 16x squared plus x to the 4th over 2 minus x cubed minus x to the 4 over 2 dx. Is this hard? No. Is it annoying?
Yeah.
Yes, it is. This is the difference between hard and annoying. So next time you're trying to explain to someone the difference between hard and annoying, please show them this problem. Right? 2-page calculation for no reason whatsoever, which is why we have computers today, right? Wolfram Alpha this, right? See, the only thing, guys, you want to make money, you need to be able to set this up as an engineer. That's your job. Calculating this, we have machines, right? So, who cares? 0 to 2. I have 8x minus 2x cubed minus x to the 4 over 2. Then divide all of these. I have minus plus 64, that's 32. And then minus 8 x squared plus x to the fourth and minus x to the 4 over 2. That's gone. So I'm just going to erase this part. There we go. Move this over. And dx. And now we just need to integrate this. That's 4x squared minus x to the 4 over 2 plus 32x minus 8x cubed over 3, calculated from 0 to 2. Kill me now. That's 416 minus, that's, what is this? Now, x to the 4th is 16 over 2 is 8, right? Plus 64 minus 8 times 8, 64 over 3. Wow. 8 minus that's 8. And 64, that's 128 over 3. And then this is 24, so 152. Right, let's say this is good, all right? And just move on. There's more cool. Wait, what time was?
7 minutes ago.
Really?
Yeah, time flies ago.
I was out to go to up to 50. Well, I'm not done with this stuff. Oh, if you want to go, bye. And then we'll continue next class then. Bye. This is not done.